I will talk about cross-sectional chemical nanoimaging of composite polymer nanoparticles by infrared nanospectroscopy. And to talk about, first let me introduce the motivation of this work. Polymer latexes are polymer nanoparticles dispersed in water and stabilized by surfactants, right? And they have been substituted in solvent-based systems, and these water-based systems are now key ingredients for many industrial relevant applications, such as paints, coatings, adhesives, or cosmetics. The performance of these particles, among other factors, of course, critically depend on the chemical composition and on the morphology. For instance, if we have two components, one is a low TG monomer like butyl acrylate and the other is a hard one like styrene, depending on the composition, we might have a sticky composition and a sticky polymer that will be used for an adhesive, or a non-sticky or harder one that will be better for a coating. In the same way, morphology also conditions the application. For instance, hollow particles are preferred for opacifiers, while multi-lobe particles, for instance, are preferred as thickeners. Both chemical composition and morphology are the result of complex kinetics and thermodynamics that occur during the synthesis. So during the synthesis, we might end here. Depending on how we synthesize, we polymerize, we might end up with different morphologies. This is an example of the same system in which we use different conditions and we end up with different morphologies, say phase separation, core shell, and homogeneous particle, which in the end lead to different films. This was designed for a coating, and here we have more phase separation and here a more homogeneous film. The good thing is that by designing properly the polymerization, we can tune the properties. That's why it's so important to properly characterize the final particle morphology, and in order to design some knowledge-based strategies. Traditionally, to assess the particle morphology and composition, one needs to use cross-sectional TM, and for that we need to prepare thin slices. But on the one hand, we need to often to stain, because polymers are mainly composed by the same materials, so there are no contrasts, and if we are lucky, we can use positive staining to stain certain groups, and we can infer some chemical composition. But this usually is a trial error effort and leads to artifact. For cutting, we need usually also to embed, to harden the polymer and enable the cutting. But it's also well known that this embedding with other polymeric resins may lead to variations in the morphology. All these artifacts can be even more tricky, or the preparation can be even more tricky when we are dealing with multi-component particles. And nowadays, multi-component compositions are preferred because these allow us to synergetically combine different properties and thus achieve better performance or better properties, right? In spite of the efforts of more sophisticated TM techniques like tomography or high annular dark field, still the unambiguous and local precise chemical information is still elusive. And with the SNOM, we can combine high chemical sensitivity and spatial resolution, and that's why we wanted to apply SNOM to characterize a multi-component polymer particle. In this work, we characterize the polyperfluorooctyl-co-methyl-methacrylate co-butyl acrylate that I will call from now on PMB copolymer. This is an example of synergetic effect. In this system, we wanted to add a fluorinated monomer that I will call POA, because these monomers are very hydrophobic, have very nice properties, and can enhance and improve the barrier properties of our anti-corrosion acrylic-based coating. But it's very challenging to polymerize in water. So the polymerization of this system was done by our collaborators from the Polymer Institute, Materials Institute of the University of Basque Country. And as a result, we obtained these particles. This is the TM image. You can see that they look quite homogeneous. I have to say that the POA has the fluorine atom. So if gives, in this case, we have contrast in TM, that is dark in the TM, and in the high annular dark field is brighter. But in this image, you see that we observe or suggest a core shell morphology with a brighter, in this case the contrast is different, brighter inner shell composed mainly by POA, which was a bit surprising because we were expecting that the POA, that is very hydrophobic, was inside. So we use SNOM. But for the SNOM, again, we need to cut to assess the interior of the particle. And in this case, it's a bit more challenging because the embedding resins and also other polymer materials that absorb normally in the region of interest we want to analyze. So we need a method for preparation of the thin slices without a chemically embedding material. To do so, we take advantage of what we call a film formation process of these materials. These particles, once water evaporates, tend to coalesce until they form the final film. But a bit before, we have this stage, what is called stage 3, in which we have the maximum packing, but the particles maintain their identity, no? And we wanted to freeze this moment to be able to have the cutting there. To know when this moment happened, we studied the drying kinetics of the PMB latex with a multi-speckle diffusing wave spectroscopy that basically measures the Brownian motion of the particles, no? Seeing that, we know that more or less it was happening in 1.5 hours. So this is the scheme of the sample preparation. We cast the film after let it dry, and once the stage 3 is achieved, we stop the film formation by quenching by liquid nitrogen, and we took the frozen sample to the cryo ultramicrotomy. Then the cutting was taken over TM grids or silicon substrate. As you can see, this is the cutting, the TM image of the cutting after the procedure. We use, finally, the morphologies well preserved. We didn't use any embedding material. This is a universal method because it can be used for any polymer system, and we have no infrared interferences. Analyzing in more detail the morphology shown here, we see again, more clearly now, that there is a core shell morphology with a POA inner shell and acrylic-rich core or acrylic-based core and outer shell. But again, we were surprised because we didn't achieve not equilibrium morphology. So if we want to now, we analyze this by the infrared nanoimaging. To do so, we need to know here you have the reference spectra of the pure components to see the maximum absorption wavelengths you need to use. And we can see the topography, that the surface is smooth enough, so the sample preparation is well suited for SNOM characterization. And we can also observe that the core shell morphology was confirmed, because when we see in the maximum absorption of POA, we see this red inner shell. And here we have the absorption image for the acrylic system. So again, core shell morphology was confirmed. But to know the composition in more detail, we did a nano-FTIR line scan of the particle cross-section. This was done along a particle, along this line scan, and here you have the individual spectra. In this plot, we have the absorption phase, the infrared absorption, as a function of the wave number and the position. Again, we can see that the maximum absorbing points correspond to the inner shell, right? But it looks that we have things everywhere, no? So we need to analyze this in more detail, and to do so, we try to reconstruct this spectra by linear superposition of the reference spectra. So we made a set of spectra combining the both reference spectra in different weight ratios, and we reconstruct this spectra. Here you have an example of each of the regions, the inner, the core, and the outer shell, and this spectrum in gray is the reconstruction. we try to do so by minimizing the interspectral distance. As a result, we observe that, on the one hand, none of them fits to pure polymer phases, so there are no pure phases on the particle, and we obtain a compositional line profile of the POA acrylic ratio that shows us that the inner shell that contains most of the POA contains around 60%. And the other two regions that were based in acrylic still have around 30% of amount of POA. And even that this amount was slightly higher at the interior of the particle in the core. I have to note or explain here that this slight difference was not due to subsurface effects. No? You know that there is a certain probing depth, but in these cases, taking into account the thickness of the cutting that was around 180 nanometers, plus that we took really the biggest particles, we can really be sure that we are not probing any POA belonging to the inner shell below our cut. No? So we are observing indeed three different compositions that we couldn't infer from the TEM results. But let's analyze again this in more consistent way to see if this is reproducible or not. So we analyzed, we chose different particles along the cutting, and we analyzed 3 spectra in each of the characteristic region in all these 7 particles, so as we have some statistical information. What we observed is that the results were consistent and reproducible, and consistently, we have around 30% of the POA in the core, 65% in the inner shell, and a bit smaller in the outer shell. So the results were, again, reproducible, and I didn't mention because we have no time, but after the synthesis, we also collect some kinetic data. We follow the unreacted amount, the amount of unreacted monomer, and these data were consistent with the kinetic result. Interestingly, they also show that there is a substantial amount of POA in the outer shell, and this shows us that the POA was underestimated at the end of the reaction. So, to summarize, I will say that we demonstrate level-free chemical identification of particle cross-section by a nano-FTIR. For that, we develop a universal method that is preserving morphology and can be used also for other techniques, and that allowed a very detailed compositional analysis that cannot be obtained by the combination even for TM or kinetic data. And more important, as a result of the information we got, we were able to tune easily this is the feeding strategy of the first system, but at the end we were able to modify to obtain fully homogeneous particles and a core shell particle containing the POA inside. And to end, I would like to thank all of you, and of course to Ivana Menabar and Rainer Hillebrand and all Nano-Optics group, and to our collaborators in Polymat, Stefano Cimenti, Maria Paulis, and José Raleiza. And thanks.